Welcome everybody once again. So we are in our 8th class for module 6, that is plastic analysis of structures. This is our last class for this module. So with this we will be completing our syllabus. Okay, in the previous classes we saw the basics of plastic analysis of structures, about the shape factor, what is collapse load, what is plastic moment, plastic hinges, etc. And we saw some 9 problems. So the first 7 problems we saw about analysis of continuous beams, and the last 2 problems were analysis of frames. Now listen carefully. In the 7th video, in the 7th class, I made a mistake. While explaining, I told you when you are considering the frames, you have to take the plastic moment of beams. So it is not like that. See, when you are considering the frames, you will have both column beams and columns. So if you are taking this joint, if you are taking this rigid joint, you consider the plastic moment of this beam and plastic moment of this column. So compare these both. Whichever is lowest, you take that value for this rigid joint. Similarly, when there is a plastic hinge at this joint, consider the plastic moment of beam, this beam, as well as the plastic moment of this column. So whichever is lower, that moment, that plastic moment you have to use for this plastic hinge. Okay, so correct it. And now we will move on to the next problem. So our 10th problem is determine the collapse load for the frame shown in figure. So the given frame ABCD. So we can draw the frame. So this is your given frame ABCD. So the supports A and D are given as fixed support. Now this joint is B and this joint is C. The span AB is of length 3 meter. The span CD is of length 4 meter. The span BC is of length 4 meter and there is a concentrated load of WO acting at the mid of the span AB. So let us take this point as E. So BE is 2 meter and EC is 2 meter. Now there is another concentrated load of WO acting at the joint B towards the right. So this load is W. Now the plastic moment are given as for the span BC, for the beam the plastic moment is 2 times MP and for the column the plastic moment is MP. Now for this column CD also the plastic moment is MP. Now you can compare. See, for the column the plastic moment is least value. That means when you are considering the joint B, you have to consider for at B the plastic moment will be MP and for the hinge at C also the plastic moment will be MP. You have to consider the lowest value. Now we will try to solve this problem. So as usual, our first step is finding the statical indeterminacy. So this is a frame. So we know statical indeterminacy is equal to number of unknown reactions minus equilibrium equations. So here A is fixed support. So we will have 3 unknown reactions, one horizontal reaction, one vertical reaction and a moment. Similarly, at D we will have 3 unknowns, 3 unknown reactions, one horizontal reaction, one vertical reaction and a moment. Which means we will have totally 6 unknowns, 3 at A and 3 unknowns at D. So 6 unknowns, 6 unknown reactions minus number of equilibrium equations available for frames will be 3. That is sigma H is equal to 0, sigma V is equal to 0 and sigma M is equal to 0. Summation of horizontal forces is equal to 0, summation of vertical forces is equal to 0 and summation of moment is equal to 0. So our statical indeterminacy is equal to 3. Now we will see the number of possible plastic hinges. So what are the How many number of possible plastic hinges? How many plastic hinges are possible? So n will be equal to, since A is fixed support, there is a possibility of a plastic hinge at A. Now B is B is joined, okay, rigid joint. Also there is an application of concentrated load. So we will have a plastic hinge at B. Then at E, we have a concentrated load acting at E. That means there is a possibility of plastic hinge at E. Now C is a rigid joint. We will have there is a possibility of plastic hinge at C. D is fixed support. So we will have a plastic hinge at D. So total possibility of plastic hinges is 5. Now the number of independent mechanisms. So the number of independent collapse mechanisms will be equal to the number of possible plastic hinges minus statistical indeterminacy. So 5 minus 3 is equal to 2. So we have two mechanisms, two independent mechanisms, and we will have combined mechanisms also. Okay, now we will see two independent mechanisms are, one is beam mechanism and the other will be sway mechanism. Okay, beam mechanism for the span BC. Then here we don't have any other loads. We have loads only at the joint. So we will have only sway mechanism. So the two independent mechanisms are beam mechanisms and sway mechanism. So first of all, we will see mechanism 1. So our mechanism 1 is beam mechanism. So we will draw the beam mechanism first. So for when we are considering this beam BEC, so BC, B and C are the joints, right? Rigid joints. That means there is a possibility of a hinge at B, there is a possibility of hinge at C, and since there is a concentrated load at E, we know when there is a concentrated load, the maximum bending moment will occur under the load. So at E there will be maximum bending moment. That is why at E there is a possibility of plastic hinge. So we will have 3 plastic hinges. And see the plastic moment, if there is plastic hinges, there will be a plastic moment at the hinges, right? So at E, your plastic moment will be 2 MP. At B, you have to take the lowest of the beam and the column. So at B, the plastic moment will be MP. And at C, the plastic moment will be equal to MP. Because you have to take the lowest of this beam, lowest of the plastic moment of this beam and this column. Okay. Then there is a concentrated load of W acting at E. The span length is BE is 2 meter and EC is 2 meter. Okay, now we will draw the beam mechanism. So we have the beam BC. There is a concentrated load of W. The distance is 2 meter from B and 2 meter from C. So the plastic hinges will be occurring at B, plastic hinge occurring at C, and there will be a plastic hinge occurring at E. So let us take this point as E dash. Okay. So now see, you can take either, you can take this, we will first of all we will take this angle as theta. So this angle also will be equal to theta because this is concentrated load is acting at the mid of the span. Now either you can take this, you can take the rotation formed as equal to theta plus theta. Okay, this is theta plus theta. So you can take this as 2 theta, or else you can draw a horizontal line here and you can take this angle as theta and this angle as theta. So both are same, right? So the rotation formed at this hinge will be equal to 2 theta. Totally it is 2 theta. Now we will see what is this distance, because distance under the load. Okay, distance under the load, this distance will be equal to 2 into theta. 2 into theta because you have to take tan theta. So tan theta, find tan theta and take theta is small, therefore tan theta is equal to theta. So you get this E dash is equal to 2 theta. Now the plastic hinges will be at E. The plastic hinge is 2 MP because for the beam it is 2 MP. Now for these joints you have to take the least of the plastic hinge. So least of the plastic hinge between this beam and this column is MP. Here also it is MP. So at the plastic hinge at B, there will be a plastic moment of MP, and at C, the plastic moment is MP. So totally 3 hinges. Now our external work done is equal to the external load into distance under the load. So we have only one load. So it is W into distance under the load is 2 theta. So we get 2 W theta. Now the internal work done will be equal to the plastic moment into the rotation. So we have 3 plastic hinge, therefore 3 plastic moment and their corresponding rotations. So at B, plastic moment is MP into rotation is theta, plus at E, the plastic moment is 2 MP into rotation is 2 theta, plus at C, the plastic moment is MP and the rotation is theta. Now you can equate external work done is equal to internal work done. We get the collapse load will be equal to 3 times MP. So this is your collapse load as per your first mechanism. Now we will go for the second mechanism. Second mechanism is the beam mechanism. So mechanism 2 is the panel mechanism or sway mechanism. Panel or sway mechanism. Okay. So panel or sway mechanisms, that is corresponding to the frame. You have to consider the whole frame. So first of all, we will draw our given frame. So our given frame is A. This point is B. This point is C. And this support is D. Both A and D are fixed supports. We have B and C. So for sway mechanism, because of sway, this B will be shifted to B dash and C will be shifted to C dash. See, this beam will just get shifted. The distance, there will not be any change in distance. That is, if BC is 4 meter, B dash C dash also will be 4 meter. That means the load acting will be, we know there is a concentrated load of W acting in the mid of BC. So now this will be in the mid of B dash C dash. So this becomes 2 meter and this distance becomes 2 meter. Okay. Now, so now this will be moved like this. Okay. Now there is a change in distance of this length AB and DC. Now, see, we know this distance is not going to change. Okay, let us take this angle as theta. So, if this angle is theta, let us take this angle as theta 1. See, you can do it in any way. Previous problems I have told you. You can take this as theta. You can take this as theta 1, which means this B dash will be equal to, since AB is 3 meter, DC is 4 meter, B dash will be equal to 3 theta and C dash will be equal to 4 theta 1. Okay, take tan theta 1 and tan theta. So you can take this B dash is equal to C dash. You can connect a relationship between theta and theta 1. Okay, get a relationship between theta and theta 1. You can do this in this way, or else, see, this is how we have done in the previous problems, or else you can do it in other way also. That means, see, now this angle is theta. This is 3 theta. So now you take C dash. You put here as 3 theta. You give this value as 3 theta and find what is this angle. You can do it in any way. So final answer will be same because you are taking external work done is equal to internal work done. Okay. Now we will do as we did so far. So now we know B dash is equal to C dash. So from which we get 3 theta is equal to 4 theta 1, which means theta 1 is equal to 3 by 4 theta. Okay. So now see, this angle will be theta and this angle will be theta 1. Draw straight parallel line. So this angle will be theta 1. Okay. Now we will take external work done is equal to, we have two loads, right? You have one load here also. We have a concentrated load at B. So for this concentrated load, the load into distance under the load. So that is W into distance moved under the load is 3 theta. Plus you have this load into distance moved under the load is 0. For sway mechanism, distance moved under this load will be 0. So it is a 0. So you get 3 W theta. Now we will take internal work done. We know internal work done is equal to plastic moment into rotation. So internal work done is equal to, so okay, I forgot to tell this. See, there will be a plastic hinge at A, plastic hinge at D, at B and C for sway mechanism, right? See, if D is a hinged joint or simple joint, simple support, hinged support or simple support, there will not be a plastic hinge at D, as we did in the previous problems. But in this problem, both A and D are fixed support. So if A and D are fixed supports, there will be plastic hinge at A as well as at D. So what we get is internal work done. Okay, before that, we will write the plastic value of plastic moment. So at A, the plastic moment will be MP. At B, there is a hinge at B. So at B, the plastic moment is the lower of the column and the beams. So it is MP. At C, there is a plastic hinge. So the MP moment, plastic moment is lower of the plastic moment of beam BC and column CD. So it is MP. And at D, the plastic moment is MP. So our internal work done is equal to, at A, plastic moment is MP into rotation is theta, plus at B, the plastic moment is MP and the rotation is theta, plus at C, the plastic moment is MP into rotation is theta 1, plus at D, the plastic moment is MP into rotation is theta 1. Now you can substitute theta 1 in terms of theta and equate internal work done, external work done is equal to internal work done. We get the collapse load is equal to 7 by 6 MP. So this is your collapse load as per the second mechanism. Now we will move on to the combined mechanism, that is our mechanism 3. So we had two independent mechanism and one combined mechanism. So our mechanism 3 is the combined mechanism. So combined mechanism is the mechanism of, it has a combination of both beam and sway mechanism. So for this combined mechanism, how the collapse mechanism is made. So first of all, we will draw the frame, our given frame. Okay. So D is fixed support. A is also fixed support. We have rigid joint B and C. Now, see, for the sway mechanism, for the combined mechanism, we will have hinge formation at A, C, D. Also, if there is concentrated load at in the span BC, there will be a hinge at that point where the concentrated load is acting. So, first of all, see, for sway, this B will be shifted to. When there is a sway, this B gets shifted to B dash, but there will not be any hinge formation. Okay, because there is a concentrated load of WO acting at B. So the sway will be towards the right. So for combined mechanism, see, this is 90 degree. The same 90 degree will be maintained here. The same 90 degree will be maintained here. See, because so your now C gets shifted to C dash, and there will be a hinge formation at C dash. So this is your beam now. So for this beam, there will be a concentrated load of WO at the mid. So the distance is 2 meter, and here the distance is 2 meter. Now the next hinge formation will be at this point. This is E, right? So at the E dash, you will have a hinge formation. So see here, this is 90 degree. This 90 degree will be maintained here. So this is 90 degree. Therefore, there will not be any hinge formation at B. Okay, because it is just shifted. This joint is shifted to this point. There will not be any hinge formation. Now at C there is hinge formation. Okay. So now see, these both angle will be same. This is 90 degree. So we'll complete this. Okay. There will be a hinge formation at D also. So this mechanism is called combined mechanism. That is a combination of beam and sway mechanism. Okay. So our hinge formation are at A, E, C and D. Now the moments, plastic moments at hinge A is MP, plastic moment at hinge D is MP, plastic moment at hinge E is 2 times MP, plastic moment at hinge C is the lower of the beam and columns, so it is MP. Now, what about the angles? See these both angles will be same. So if this angle is theta, this angle also will be equal to theta. Okay. So what about this angle? So this angle will be equal to theta. Now this, there will be, see, because of this beam, okay, combination of beam. So if this angle is theta, this angle also will be equal to theta because this concentrated load is acting at midpoint. So here this angle will be equal to theta, theta. Now this angle is equal to theta 1. Therefore, this angle will be equal to theta 1. Now the distances. See, there is a shift in B dash, right? So this distance B dash will be equal to, so we know this AB is 3 meter and CD is 4 meter. So this distance B dash will be equal to 3 theta. Therefore, C dash will be equal to 4 theta 1. 4 theta 1. C dash will be equal to C dash will be equal to 4 theta 1. Now we know 3 theta is equal to 4 theta 1. 3 theta is equal to 4 theta 1, from which we get theta 1 is equal to 3 by 4 theta. Because this is just shifting, this just gets shifted. Okay, so B dash will be equal to C dash. So theta 1 is equal to 3 by 4 theta. Now we can go for external work done is equal to external load into distance under the load. So we have two external loads. Here W and W. So at B, it is W into distance under the load is 3 theta. At E, external load is W and distance under the load. See, this is 2. This is theta. So this distance is 2 theta into 2 theta. Now, internal work done is equal to, we have 1, 2, 3, 4 plastic hinges. So at A, plastic moment M into the rotation is theta. At B, there is no hinge. At E, the plastic moment is 2 mp into the rotation is theta plus theta. So 2 theta plus at C, plastic moment is mp, rotation is theta plus theta 1. Theta plus theta 1. At D, the plastic moment is mp, rotation is theta 1. So now you can equate external work done is equal to internal work done. We get the collapse load is equal to 1.5 mp. So this is your collapse load as per your combined mechanism, that is the mechanism 3. Now you can compare all the 3 mechanisms. So for third mechanism, W collapse load is 1.5 mp. The second mechanism collapse load is 7 by 6 mp. And the first mechanism, the collapse load is 3 mp. So when you are considering the collapse load, you have to take the least value. And when you are considering the plastic moment, you have to consider the largest value. So the least among the 3 values is 7 by 6 mp, which means for this problem, your collapse load is 7 by 6 mp. This is your answer. That means, so this is corresponding to the sway mechanism, which means your frame will fail by sway mechanism. That is the meaning of that. Okay, this is your conclusion. Your frame will fail by sway mechanism. Now we will move on to the next problem. So problem 11. So again, find the collapse load for the portal frame shown in figure. Okay. So now I think you can do this of your own. Okay, anyway, come on. Okay, your given frame is of equal length. Okay. All these spans are of equal length. You can take this as A, B, C and D. So the length are given as, the beam is of length 2L. The columns are of also of length 2L. AB is 2L and CD is also 2L. Now there is a UDL, uniformly distributed load of 5F. 5F. See, this is the total load. 5F is the total load. And there is a concentrated load of F acting at the joint B. That means your frame will sway towards the right. Also, the plastic moment is given as 2 mp for the beam BC and mp for the columns BA and CD. Now, see, you have to, if such problems are given, you have to remember One thing. That is, see, this is your total load. This 5F is the total load. When you take the external work done, if it is UDL, you have to consider the load into area under the load. So when you are considering the area under the load, you have this load into area under the load. So this load is not the total load, it is the load per unit length. Okay, so here now it is given the total load as 5F. You have to convert it into load per unit length. So this is equal to, the total load is 5F. Now this will be equal to, this is nothing but 5F by distance 2L per unit length. Okay, so you have to consider this while you are taking the external work done for this beam BC. You have to consider for external load is equal to 5F by 2L per unit length multiplied by the area under the load. Otherwise, there is a high risk, or there is a chance of making mistakes while solving the problem at for the examinations. Okay, now so I will write that first. Okay, so your load in the span BC is equal to 5F, that is equal to 5F by 2L, that is this distance of this, okay, 5F by 2L per unit length. Okay, now you have to use this 5F by 4L while taking the external work done. Okay, now you can proceed as usual, that is your statical indeterminacy is equal to R minus R. There is 3 unknowns at A, 3 unknowns at D. So it is 6 minus 3 is equal to 3. Number of possible plastic hinges is equal to, there is a possibility of plastic hinge at A, plastic hinge at B, then under BC where the maximum bending moment occurs. So this is a UDL throughout the span. So maximum bending moment will occur at the center of the span. So let us take that point as E. So at E there is a possibility of hinge, at C there is a possibility of a hinge, at D there is a possibility of hinge. So total possibility of hinges is 5. That means your number of independent mechanisms will be equal to 5 minus 3 is equal to 2. Okay, so we will have beam mechanism, sway mechanism and a combination of beam and sway mechanism. So mechanism 1 is beam mechanism. So we have a beam BC, length is 2L. It is there is a total load of a 5L, or unit load per length is 5F by 2L. And the plastic moment is 2 MP for the beam and MP for the column. Now we will draw the beam mechanism. Okay, our beam is BC. BC, there is a constant unit load, there is a UDL, right, of 5F by 2L per unit length. So there will be a hinge formation at B, hinge formation at C and hinge formation at E. Okay. So if you take this angle as theta, this angle will be equal to theta. So work done here will be theta and theta. Rotation is theta and theta. And this distance, see this is 2L. Total length BC is 2L. That means BE is L, right? BE is L and EC is L. Which means this distance EE dash will be equal to L into theta. Now our external work done is equal to load into distance under the load. Here it is UDL, so load into area under the load. So magnitude is 5F by 2L per unit length multiplied by area under the load is, it's a triangle, right? Half into base is 2L into height is L theta. Now, internal work done is equal to plastic hinge, plastic moment into rotation. So, here at B, the plastic moment is the lowest of the beam and column. So, it is MP. At C, it is lowest of the beam and column. So, MP. At E, it is of the beam. So, it is 2 MP. So, at E dash, the plastic moment is 2 MP. So, internal work done is equal to, at B, it is MP into theta. At E dash, it is 2 MP into theta plus theta. So, 2 theta plus at C, it is MP into theta. Now, you can equate external work done is equal to internal work done. We get the collapse load is equal to, so here collapse load is in terms of F, right? So, your collapse load F will be equal to 2.4 MP by L. So, this is your collapse load as per your first collapse mechanism. Now, we will move on to the mechanism 2. So, mechanism 2 is the sway mechanism, sway or panel mechanism. So, for that, first of all, we will draw our frame. Frame is of equal length, right? Fixed supports A and D. So, now there is a concentrated load, right? So, this is B and this is a C. Now, for the mechanism, B gets shifted to B dash. There will be a hinge formation at B dash. C gets shifted to C dash. There will be a hinge formation at C. There will be hinge formation at A and there will be hinge formation at D. So, your frame will be like this because of the sway mechanism. Your frame will become like this, right? Okay. So, now we have a UDL of 5F by 2L per unit length. There is a concentrated load of F acting at B. So, AB everywhere the length is 2L, right? AB is of length 2L. BC is of length 2L. So, now this distance B dash will be equal to C dash. Also, if this angle is theta, so this angle becomes theta. Both columns are of equal length. So, this angle also will be equal to theta. Now, B dash is equal to 2L theta. This is 2L theta. C dash is equal to 2L theta. This is 2L into theta. Now, external work done is equal to this load at B. F into distance under the load 2L theta. Here under this concentrated load, under this UDL, there is no area, right? So, that's all. Now, internal work done is equal to hinge formation. Hinges into, this hinges into, that is plastic moment into rotation. So, at A, the plastic moment is MP. At B, the plastic moment is MP. Take the lowest of both column and beam. At C, the plastic moment is MP. Take the lowest of the beam and the column. At D, the plastic moment is MP. So, internal work done is equal to, at A, it is MP into theta. At B, it is MP into theta. At C, MP into theta. At D, MP into theta. Now, external work done is equal to internal work done. we get the collapse load F is equal to 2 MB by L. This is our collapse load as per our second mechanism. Now we will move on to the mechanism 3. So mechanism 3 is called combined mechanism. That is a combination of beam and sway mechanism. Combined mechanism, combination of beam and sway. So we will draw our frame first. So for the third mechanism, we will draw the frame first. So we will draw the given frame. Okay, so our A is fixed. Support D is also fixed. We have supports B and, rigid joints B and C. Now, for the beam sway mechanism, this B gets shifted to, B dash, but there will not be any hinge formation. So this 90° will be maintained at this point, B dash also. C gets shifted to C dash, but there will be a hinge formation at the C dash. Also, there will be hinge formation at A since it is fixed support. There will be a hinge formation at D since it is a fixed support. Okay, now there is a UDL, right? There is a UDL in the span BC. So this UDL is 5F by 2L per unit length. Now this distance AB is 2L and the distance BC is also 2L. Similarly, the distance CD is also 2L. So now this is a symmetric beam, right? But we have a concentrated load of F. Concentrated load of F acting at B. So which will make the frame to sway towards the right. So now, our frame will be, the mechanism of the frame will be like this. Also, here there will be 90°. There will be a hinge formation where there is a maximum bending moment. Let us take that point as E dash. Okay. Where is maximum bending moment? We don't know where the maximum bending moment occur. The reason is when we have taken the beam mechanism, at B also there was a hinge, at C also there was a hinge. So your bending moment, maximum bending moment will occur at the mid of the span. But for this case, see, when there is a concentrated load, even if there is no hinge formation at B for the sway beam mechanism, the maximum bending moment will occur under the load. But here, since it is subjected to UDL, the maximum bending moment will not occur at the mid of the span because there is no hinge at B, there is only hinge at C. That means your bending moment will occur at some place but not at the mid of the span BC. So you have to find at what point your maximum bending moment will occur. Okay, before that, the possible data we will mark it. That is, see, this column beam is 90°. The same 90° will be maintained here. Okay, that means this angle is theta. This angle also will be equal to theta. Now, since there is no hinge at B and there is only hinge at C, this angle will be equal to, let us take this angle as theta 1. Now, since AB and CD is of equal length, this angle also will be equal to theta. But this angle is theta 1. Now, B dash will be equal to CC dash. Okay. So B dash will be equal to C dash, which means B dash is 2L into theta. Here also it is 2L into theta, right? So that is equal to 2L theta. So this distance is 2L theta, B dash is 2L theta, and C dash is 2L theta. Now this angle is theta, and this angle also will be equal to theta because this is theta, this is theta. Now when we draw a parallel line towards BC, this angle is theta, but this angle is theta 1, alternate angles. This is theta, theta, theta 1, theta 1. So now we need to find what is theta 1, what is theta, etc. So let us take our maximum bending moment occur at a distance of, at this point, right? That is at a distance of x from B. Let us take this distance as x. So that means, okay, we'll take it in another color. Let us take this distance, that is our maximum bending moment is occurring at a distance of x from B. So that means this distance is equal to, that is distance under the point where the maximum bending moment occur is equal to, this is x theta. This is also equal to, see this is x theta, this is also equal to, so if this is x, this distance is 2L minus x, right? So this distance is also equal to 2L minus x into theta 1. Both are same. So we know x theta is equal to 2L minus x into theta 1, from which we get theta 1 is equal to x by 2L minus x into theta. Now we can take external work done and internal work done. So external work done is equal to the load into distance under the load. So F at B, it is F into distance under the load is 2L theta. This distance is 2L theta. Plus, there is another UDL, right? So load into area under the load. So 5F by 2L into area under the load is half into base is 2L into height. So this height is x into theta. So x into theta. Now internal work done is equal to the plastic moment into hinges. So at A, the plastic moment is equal to MP. At E, plastic hinges 2 times MP. At C, plastic hinges MP. At D, the plastic hinges MP. So internal work done is equal to at A, MP into theta, plus at E, 2 MP into theta plus theta 1. This is theta 1. So theta plus theta 1 plus at C, MP into theta plus theta 1, and at D, it is MP into theta. Now you can equate external work done is equal to internal work done. So when you equate external work done is equal to internal work done, we get MP is equal to 4FL square plus 3FLX minus 2.5FX square divided by 10L minus 2X. So you have got this MP in terms of F, load, length L, and another one variable as X. So now you need to find X, that is where the maximum bending moment occurs. So for finding the maximum bending moment, that is for this MP to be maximum, that is differentiate MP with respect to X. So dMP by dx is equal to 0. Now you can differentiate MP with respect to X. So what we get is, this is of the form U by V, right? So we know differentiation of the form U by V is equal to U into differentiation of dV by dx minus V into du by dx by V square. So in the numerator we get, in the denominator we get 10L minus 2x the whole square, and in the numerator it is U into. Sorry, it is V into du by dx. U into dV by dx, right? So V is 10L minus 2x. V is 10L minus 2x into differentiation of the numerator. So we get this is 0. Here it is 3FL minus 2.5 into 2. So 5 Fx minus numerator into differentiation of the denominator, that is 4FL square plus 3FLX minus 2.5 Fx square into differentiation of denominator, that is minus 2 is equal to 0, from which we get x is equal to, you can expand this, you will get x is equal to 0.829 L. Now you can substitute x is equal to 0.829 L in MP. Take this as equation number 1. So substituting in equation number 1, we will get MP is equal to 0.572 FL. So now you can compare, which means, so from which you get F is equal to, that is collapse load is equal to MP by 0.572 L. So that is nothing but MP by, 1.75 MP by L. So now you can compare. So this is the collapse load from the third mechanism. So you can compare all the three mechanisms. You will get the least load as 1.75 MP by L, which is your collapse load, which means your frame fails by the combined mechanism. Combined mechanism, that is mechanism of beam and sway. Beam plus sway mechanism. That's all. So the next problem, I will give you the question. You can try to solve the problem. So that is also similar to this problem what you have solved now. Okay. 12th, the last problem is, I will give you the question. Find the collapse load. So A is fixed. D is also fixed. Both are of unequal length. There is a concentrated load of WU by 2 at a distance of 3 meter from A. So this is also 3 meter. So A, B, C and D. In the span BC you have a UDL of WU by 6 per unit length. And CD is 7 meter. The span BC is of 6 meter length. Also the moment is, for the span BC, the moment is MP. For the column AB, the moment is 0.8 MP. And for the column CD, the plastic moment is 0.8 MP. So that's all. You can solve this as your own. I will give you the answer. The statical indeterminacy for the problem is 3. The number of plastic hinges possible are 6. Therefore, the number of independent mechanisms will be equal to 3. So, first mechanism will be beam mechanism. So, for beam mechanism, after equating external work done is equal to internal work done, you will get the collapse load is equal to 2.4 into 10 raised to 5 Newton. So, the second mechanism will be column mechanism, because for the column AB, you have a concentrated load acting at the mid of the column AB. So, in AB, you will have a column mechanism similar to that of beam mechanism. So, second is column mechanism. So, for the column mechanism, after equating the external work done is equal to internal work done, you will get the collapse load is equal to 2.13 into 10 raised to 5 Newton. Third mechanism is the sway mechanism. So, sway mechanism you will get. See here, the columns are of unequal length. So, you will have theta 1 and theta 2. And equating external work done is equal to internal work done, we will get our collapse load is equal to 1.98 into 10 raised to 5 Newton. And the last is the combined mechanism. The combined mechanism is a combination of beam and sway mechanism. So, for this mechanism, you will get the collapse load. So, here, see, since our beam is subjected to UDL, you have to find the distance where the maximum bending moment occurs. And after that, finally, you will get your collapse load as 1.62 into 10 raised to 5 Newton. And the least will be the for the collapse load for the combined mechanisms. That means your frame will fail by the beam and sway mechanism, that is the combined mechanism. So, with this our sixth module has been completed and our syllabus is completed, and all the best for your exams. Study thoroughly, prepare thoroughly, and write your exams in confidential manner. Thank you and all the best. Thank you.